Welcome to section 9.5. This is the 76th session of the CISSP exam prep series. In this session, we'll look at how servers move data and share heavy workloads. We'll answer several questions. What is data flow control and why does it matter? How does a load balancer help? How do parallel systems split enormous work? What makes grid computing risky? And where does peer-to-peer fit? Why does this matter beyond the exam? Because a server that cannot manage its own traffic will collapse under load, whether from an attack or its own success. Picture a ticketing platform on the morning a major concert goes on sale. Millions of requests arrive at once. On the job, you design how that flood is throttled, spread, and absorbed. Get the flow wrong, and the service falls over exactly when it matters most. So what is data flow control, and why does it matter? It is the management of how data moves between processes, across networks, and over channels. Done well, it keeps transmission efficient with low latency, reliable through integrity checks, and confidential through encryption. Crucially, it also keeps receiving systems from being swamped past the point where they drop connections. When data overflows, it can be lost, corrupted, or forced into costly retransmission. So, flow control exists to prevent exactly those failures, and it is provided by devices like routers and switches, as well as network services. Think of a highway with metered on-ramps. The signals release cars at a steady pace so the road never seizes into gridlock. How does a load balancer help? It spreads incoming traffic across several links or servers so no single one is overwhelmed. The goal is better use of your infrastructure, faster response, higher throughput, and no bottlenecks. A common deployment fans requests out across the members of a server farm using techniques like round robin, random choice, or watching real-time utilization to decide where each request goes. Think of a busy checkout area where a coordinator waves shoppers to whichever register has the shortest line. No single cashier drowns while others sit idle. What happens when traffic is malicious? You face a denial of service attack, which can cripple data flow control outright. By flooding a system with bogus traffic, an attacker aims to exhaust its capacity so legitimate users cannot get through. This is why you monitor for these attacks and build in mitigations before they strike. Think of pranksters jamming a pizza shop's phone line with fake orders. Real customers hear a busy signal, and the kitchen grinds to a halt. How do parallel systems split enormous work? They break a huge task into smaller pieces and hand each piece to a different processor to compute at the same time. There are two broad camps. In symmetric multiprocessing, several processors share one operating system, one data bus, and common memory, working together on a single main task. In asymmetric multiprocessing, each processor often runs its own operating system and owns its own memory, and specific tasks can be pinned to specific processors. An arrangement called affinity. A more extreme variation links many asymmetric systems into a massive cluster with hundreds or thousands of processors, ideal for the heaviest scientific and mathematical workloads. Think of a single large team all reading from one shared plan versus a network of independent crews, each running their own playbook on their own slice. What makes grid computing risky? Grid computing loosely pulls many volunteer nodes that join and leave freely, often lending spare capacity while their machines sit idle. That openness is exactly the problem. Because anyone can participate, the contents of each work packet may be exposed to the world, and members could keep and inspect copies. So grids are a poor fit for private or proprietary data. Capacity also swings wildly, and packets can come back late, corrupted, or not at all, which hurts time-sensitive projects. And because a grid leans on central servers to coordinate, overloading or knocking those out can bring the whole thing down. Think of a giant crowdsourced puzzle where anyone can grab a piece, fast and cheap, but you can never be sure who saw the picture or whether they will return their piece. Where does peer-to-peer fit? Peer-to-peer solutions share tasks and workloads directly among equal nodes with no central manager, and they usually deliver service in real time rather than pooling raw computation. Common examples include many voice-over internet services and file distribution tools. The security worries are distinct. There is the pull toward pirating copyrighted material, the chance to eavesdrop on distributed content, the absence of central oversight and filtering, and the risk that the service devours all available bandwidth. Think of an open neighborhood tool lending ring with no librarian. Convenient and direct, but nobody is checking what gets passed around or how much it strains the block. So let's bring it together. Data flow control keeps traffic efficient, reliable, confidential, and, above all, from overwhelming the receiver. A load balancer spreads that traffic so no single server drowns, while a denial of service attack tries to force exactly that drowning. Parallel systems divide massive work, symmetric sharing one brain and asymmetric running many, scaling up to huge clusters. And grid and peer-to-peer models pull distributed effort cheaply at the cost of exposure, inconsistency, and lost central control. Match the model to the sensitivity of the data, and you keep both performance and protection. The MCQs covering all the topics and concepts from this session are available on rucloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session.